Bringing back to the circumgalactic medium, we have Nikki and Nielsen from Swinburne University telling us about directly imaging circumgalactic medium structure at the 30 kpc from a starbursting galaxy. Take it away, Nikki.
All right. Yep, and everyone can see my slides just fine.
Looks good.
Okay. All right, so yeah, thanks for the introduction, and yeah, taking it back out to outside of a galaxy rather than the really small things inside of a galaxy. So today I wanted to highlight some results where we've used KCWI to measure some CGM structure in emission from a starbursting galaxy. And this work is in collaboration with all the people I've listed here on the slide, but I wanted to highlight Deanne Fisher and Ryan Rickards-Bott because they both had posters in poster session B. So if you haven't had a chance yet, do take a look at their work because it's relevant. All right, so Hasti had a nice introduction of the CGM, but just to be sure everyone's on the same page, we know that galaxies, in order for them to sustain their star formation, they must accrete fresh gas from the IGM. And this gas comes in along the major axis, it tends to be metal poor, and it adds angular momentum to the disk. That gas will then eventually form stars, and those stars will eventually eject metal-enriched gas back out into the CGM. And some of that material will fall back onto the galaxy as recycled accretion, and it will just cycle in and out. But some of it will stay within the CGM, and some of it for the lowest mass galaxies will actually escape the galaxy. We also know that galaxies eventually stop forming stars, and to do that, they have to stop accreting that fresh gas from the ISM. And so when they do that, they then expend their star-forming reservoir in the ISM and become quiescent. So these gas flows, and whether they're active or not, make up the baryon cycle, and the CGM hosts all of these gas flows. And so in order to understand how galaxies evolved to what we see today, we must understand what the CGM looks like. So this is just an artist's illustration, and what we've done here is the gas flows look really smooth, but we know from observations of M82 that the outflows definitely are not smooth. There's lots of little structure in them, but also simulations suggest that the CGM is made up of many sub-kiloparsec size clouds. There's several simulations that have found this with much higher resolution in the CGM. And so the structure in the CGM is much more complicated than our simple picture showed. We also know that the widely used quasar absorption line method that Hasti used, while it provides a wealth of information, it is very difficult to measure the sizes of these clouds without making a bunch of assumptions and doing some photoionization modeling. But fortunately, we can maybe start to understand the sizes of these things by directly imaging the gas flows in the CGM using emission and with new instruments like KCWI. So we know that the CGM is observable. Several groups have already observed it, mostly the large-scale structure. So these are just 5 examples spanning a redshift of about 0.45 all the way up to redshift 4. Typically, you only have about 1 emission line where you can measure the CGM, and you find a wide variety of structures. But these maps are still missing the small-scale structure predicted in simulations. And so the way we can kind of solve that problem is to move to lower redshift and start looking at the CGM around nearby galaxies where you can get the sub-kiloparsec scale resolution you need. So that's what we are doing with the Duvet survey. So Duvet is more of a general survey looking at the galaxies themselves. So with this program, we aim to test star formation theories, map multi-phase outflows, and I've bolded this next section because it's most important for this talk, but we also aim to trace the transfer of gas between the ISM and the CGM, and we do this with KCWI for the most part. So what we do is we observe disk galaxies, and we measure the outflows in a specific region, and we map those outflow properties to the star formation activity and properties. So we have built up a sample of about 30 galaxies that are local analogs of redshift 1 to 3 star-forming galaxies. And you can see from the plot on the right that these galaxies are starbursting. They have a star formation rate that is much greater than the main sequence of galaxies at the same redshift. And they span a wide range of stellar masses. We also know these galaxies are disks, so they haven't undergone a major merger very recently. So their active star formation is actually due to more of a very large accretion event rather than some very strong interaction. So these are 3 of the galaxies in our survey. These are very pretty and very face-on, but we do also have some edge-on galaxies in the sample. And if you're interested in seeing how we can trace the accretion and outflows from an edge-on galaxy, I encourage you to look at Deanne Fisher's poster. She's PI of Duvet, and she's just presenting the first paper from the program. It's really interesting stuff. But today I'm going to focus on our pilot galaxy, which is RS-08, and it's at a redshift of 0.02, so it's very nearby. And it's a face-on galaxy, and it has a stellar mass of 10 to the 10 solar masses. So we know that RS-08 is starbursting. That's kind of the criterion for being included in the sample, but it has a star formation rate of 10 solar masses. And we know from work that Braunreichert Schuh has done, so she's a PhD student here at Swinburne and gave a talk last year at the Keck Science meeting. But she's mapped out the outflows in the disk of this galaxy, and she found outflows across the entire disk. So normally when you think of a starbursting galaxy, you think of M82, which has bipolar outflows coming from the center of the galaxy, but she's finding these outflows everywhere. So it's intensely starbursting, and we know that RS-08 is a low metallicity galaxy. It has a metallicity that's about 5 times lower than is typical for galaxies of its mass. And so this suggests that it's actively accreting metal poor gas, both for its star formation and to dilute the ISM metallicity. Fortunately, we do have some VLA data of this field. And so we see a large H1 plume, which if you were to measure this with quasar absorption lines would be detected as a DLA. But it's located between RS-08 and a much smaller companion galaxy that's nearby. And so we think that RS-08 is actually accreting this H1 plume of gas. And so given KCWI and that we can observe the CGM in emission, we decided to try and map this gas flow to determine its properties. So you can see here is a PanStars image of RS-08 and then its surroundings. And this blue rectangle at the center shows our primary Duvet pointing that we used for bronze work. But then we also were able to do an additional 4 pointings with KCWI, and we spent 2 hours on each of these pointings. 3 of the pointings sit on the H1 plume, and then there's a 4th that we used as more of a control field. And here are the surface brightness maps for the 035007 line, and we find emission everywhere. I will note that I did some Voronoi binning here to get a signal to noise ratio greater than 5 in every bin. And so every bin has detectable signal in 03. So this was exciting, perhaps not so surprising given some of the other work. But the benefit of our work is not only do we have higher spatial resolution, but we also cover multiple lines. So I've already shown you the 035007 line, but we also have the O2 doublet and the H beta line. And so we can look at the surface brightness profiles, and we see that the surface brightness very rapidly decreases as you move off the galaxy. And then it levels off into the CGM and remains fairly level out to about 30 kiloparsecs away from the galaxy. And we see this in all of our lines as well. So given that we have multiple lines, we can do things like measuring the ionization of the gas. So we took the ratio of the O3 to O2 line, which gives you an idea of how ionized the gas is. And we found a general trend of increasing ionization as you move away from the galaxy. This result is consistent with higher redshift work looking at the CGM with absorption. So that's not unexpected. There may be some azimuthal variation where if you compare the orange and green points to the red and purple points, there's a little bit of an offset, but we're not entirely sure what that's due to just yet, so stay tuned. But perhaps the more exciting result here is that if you look a little bit more closely at both the CGM portion of the surface brightness map and the maps themselves, you might see these very small, very bright bins. And in fact, that bright one is actually this green point over here. So they stand out quite a bit. And we found quite a few of these bins that are brighter and smaller than their surroundings, and they have a diameter of about 500 parsecs. So we weren't expecting to find these, but we thought of a couple different scenarios that could explain what these knots are. And we thought of, well, every galaxy is expected to have some satellites, so perhaps these are dwarf galaxies. And in fact, looking at the maps, there are a couple knots that are next to each other. So they could actually be a single object, but the PanStars imaging we have right now does not show any dwarf galaxies, but it is limited to the seeing because it's ground-based observations. These objects could also be external H2 regions. Some other groups like Work et al. And I think Chris Hauck as well has found these star-forming regions that are outside the disk of galaxies. So we could be seeing some star formation in a tidal stream that's accreting onto IRS-08. Or I think this one's most exciting because I'm a CGM person, but these could be the cool accreting CGM clouds that are predicted in simulations. So this would be gas that's condensing out of a hotter medium and forming these sub-kiloparsec clouds. No one has found these yet, but perhaps we have. Unfortunately, our KCWI observations cannot distinguish between these three scenarios, but we were just awarded 5 orbits of HST time during this last cycle. So we will be measuring H-alpha and stellar continuum of these knots in the very near future to try and distinguish between the 3 scenarios. So I hope by the next Keck Science meeting, I'll be able to already have an answer for what those knots could be. But also, we do have additional Duvet galaxies where we've already measured some of the CGM emission along both the major axis and minor axis of an edge-on galaxy in particular. So please stay tuned because there's more exciting results to come. Thanks.
Thank you, Nikki. Questions? Let's start online. Okay, I don't see any. Any questions in the audience?
Well, I'll take a question for Nikki here. So aren't you concerned that your field, the sample field, is actually not empty, since it didn't show anything in the VLA data?
Sorry, it's really echoey. I heard, yeah. Am I concerned about the central pointing? What was the rest?
Yeah, so the test field there, I think it's P4, but the VLA data doesn't show anything, and here you get a lot of emissions. So is that a concern, or what do you explain that?
I think I understood, because I had a similar thought. So you had one field that was a calibration field that was sort of off to the side, where there was no I think it was H1 signal. And I think Dimitri's question is, are you concerned at the fact that you see emission in this field, even though it's sort of a calibration field off to the side, or is that expected? I think that was the question.
That seems, I think you're right. I don't think it's a concern because the VLA data, the H1 measurement is quite high, but typically the CGM can go quite low. So we use that control field to see if we needed very strong H1 or not. But given that we see it off here, and then other groups have also seen CGM basically everywhere, I don't find it concerning. It's just a matter of how do the properties differ where we see that H1 plume versus not. And that's something we're still working on. And in fact, the knots will probably be important for that as well.
Okay, we have a question online. First, great talk. Have you compared the metallicity of the CGM/gas flows and ISM of the galaxy?
Yes, so I have a plot down here where we've kind of done a bit of a metallicity measurement using R23, where it's the O3 plus O2 divided by H beta, and it shows it's relatively flat. But I think right now it's really difficult to measure the metallicity of this gas because the R23 parameter relies on having H2 regions. And for all we know, we don't have H2 regions in the CGM. So I think you should really take this result with caution for right now. But if you look at the CGM and absorption, you can do a little, you can measure an ISM metallicity and get the metallicity in the CGM with a point source. So it's a very small region, but there's not really any general trends of like a clear decrease as you move outwards. Metallicities are still quite tricky in the CGM for now.
We have one more question here. Can you hear us?
Yep.
We'll try.
Nikki,
Go ahead.
How about velocity structures in this gas?
Velocity structures. Yes, I also have that. So this was just a quick map that I made to look at it. I think also take this with caution because this is a very face-on galaxy. But I think the thing you can really be interested about is like those very small bins sometimes have very different velocities. So like this one out here is very blue shifted relative to its surroundings. If we had a more edge-on galaxy, I could tell you more about whether that gas is really accreting and rotating with the galaxy or not. But this one's, it's just a little bit too tricky for that.
Okay. Okay, I think, thanks again, Nikki. Let's thank again, Nikki, for a great talk. I think